Welcome to Robo's Physics Adventures. Today Robo will be learning about error propagations. Today Robo is doing some volunteering work with its classmates. Robo is about to put the work done by grade 1 to 5 students on the school wall. The work done by the students have a width of 15 plus or minus 3 centimeters and a height of 20 plus or minus 5 centimeters. Mr. S has told students that the size of the school wall is 60,000 plus or minus 10% centimeters squared. Robo wonders how many student work can go on the wall. Robo also wonders what it means to have an uncertainty represented by a percentage. Mr. S says, we express uncertainty in 3 different ways. So far, we have seen the absolute uncertainty. For example, for 15 plus or minus 3 centimeters, the 3 is the absolute uncertainty, and it tells us that most of the measurements are 3 centimeters more or less compared to the average measured value of 15 centimeters. The symbol used to show the absolute uncertainty involves a delta or a triangle sign. This sign represents change. For example, if the measured value is A is equal to 15, the absolute uncertainty is delta A, which is equal to 3, which again means 3 more or 3 less. Uncertainty can also be expressed in forms of a fraction or a percentage. To find the fractional uncertainty, we divide the absolute uncertainty by the measured value. In this case, it would be 3 divided by 15, which could be expressed as 1 over 5 or 0.2. We can then turn this into a percentage uncertainty by multiplying the fractional uncertainty by 100%. Here we will get 20%. We often either write the measured and uncertainty together using absolute or percentage uncertainty. We don't often use fractional uncertainty in writing as it could get confusing since it looks similar to the absolute uncertainty. Robo thinks out loud. So 60,000 represents the measured value and the 10% is the percentage uncertainty. 10% is 10 over 100 or 0.1, and this must be the fractional uncertainty. That would mean that the absolute uncertainty divided by the measured value is 0.1. If we multiply both sides by A, we would get that the absolute uncertainty is 0.1 times the measured value. Here, that would be 6,000. And that would mean that the size of the wall is 60,000 plus or minus 6,000 centimeters squared. Mr. S confirms Robo's thoughts. Robo then calculates the maximum area of pictures made by the students by multiplying the upper bound of both values to get 450 centimeters squared. Robo calculates the minimum area by multiplying the lower bound of both values, which are 12 and 15, to get 180 centimeters squared. The maximum area of the wall is 66,000 centimeters squared and the minimum area is 54,000 centimeters squared. To find the maximum number of work that can be put up, Robo divides the maximum wall area by the minimum student work area to get approximately 366. Robo then calculates the minimum number by dividing the minimum wall size by the maximum student size work to get approximately 120. Mr. S confirms that the logic is correct. Mr. S suggests an alternative method for finding the number, one that involves fractional uncertainties. Mr. S says that this is one method of calculating the uncertainty. In this method, when you add or divide measurements, you simply add their fractional uncertainty. An alternative method to this, and one that is used often, is adding the square root of the fractional uncertainties squared, but we'll use the easier method here. Robo thinks that the fractional uncertainty of the width is 3 over 15 or 0.2, and the fractional uncertainty of the height is 5 over 20 or 0.25. That would mean that the fractional uncertainty of the multiplied valued would be the addition of 0.2 and 0.25, which is 0.45 or 45%. This would mean that the area is 15 times 20, which is 300, and its percentage uncertainty is 45%. It's fascinating how much the error has grown. To find the number of photos, Robo has to divide the area of the wall by the area of the student work. 60,000 divided by 300 gives 200. Robo adds the percentage uncertainties of the numbers, which are 45% and 10%, to get 55%. Therefore, the number of photos based on this method is 200 plus or minus 55%. Robo knows that 55% is equivalent to 55 over 100. By rearranging for the absolute uncertainty, Robo determines the number of photos to be 200 plus or minus 110 using this method. Comparing this method to the original method has produced very different values. Mr. S confirms the observation. Mr. S says that the original method produces an average of 243, which is slightly higher than what's expected. The method that Robo just learned and the one that Mr. S discussed earlier is a better representation when using correct statistics methods. Every method does have its own limitation that will be discussed further during the statistics course. Robo asks, what if you use exponents? Mr. S says, imagine you have a cube with measurements of 50 plus or minus 10%. The volume is length cubed. This is 50 cubed or 125,000 units cubed. When you add the fractional uncertainty, you will have to do it 3 times because you are multiplying the length by itself 3 times. This is same as multiplying the fractional uncertainty by the exponent value, which is in this case 3. Therefore, when dealing with exponents, the fractional uncertainty of the measurement is multiplied by the value of the exponents. Mr. S asks Robo, do you remember how to calculate the uncertainty when you add and subtract measurements? Robo asks Mr. S to provide a reminder. Mr. S said, imagine that there are 3 blocks that are stacked on top of each other with a total height of 18 plus or minus 3 centimeters. If we took out one of the blocks with a height of 5 plus or minus 1 centimeters, what would be the remainder? After processing this, Robo said, well, the maximum possible value would be the maximum total height, which is 21, minus the minimum height of the block removed, which is 4. This would give us 17 centimeters for the max. To find the minimum total, we would use the minimum total height of 15 minus the maximum block height of 6 to get 9 centimeters. Mr. S confirmed the logic and then said that there is another method, which is to add the absolute uncertainties of the 2 values. Therefore, the difference is simply 18 minus 5, which is 13 centimeters, and the absolute uncertainty is 3 plus 1, which is 4 centimeters. This would give the upper bound to be 17 and the lower bound to be 9, similar to your calculation. In general, when adding or subtracting values, you would add the absolute uncertainties. Robo agreed that logically that would make sense. Robo asks if this is all they need to know in terms of adding and subtracting measurements. Mr. S said that there is one last concept. When you add 2 numbers, your final answer can only be as good as the number with the least number of decimal places. Robo said, well, that makes sense because by displaying more decimal places, it seems as though we know more about the final value. The number could only be as good as the weakest link. Mr. S confirmed that this is true. He then said that when you multiply or divide, your final value will have as many significant figure as the lowest one in your calculation. For example, if you were to multiply 10 by 14.1, you would get 141. But the value of 10 could have been rounded down from 14.44 or rounded up from 5. We are only certain about this value to one significant figure, and therefore we need to round our final answer to one significant figure as well. It's important to use an approximation sign whenever we round a value. Robo recorded these rules in its memory. This was the last part of the lesson for measurements. These are some of the basic skills that Robo will have to use throughout physics. There is much more to measurements, and it's important to explore these concepts using lab skills at school and at home. Robo is going to get some rest before starting the next journey in mechanics. Robo hopes that you have learned some of the basics of measurements in watching its first part of the journey, and hopes that you join it for its future adventures.